Welcome to this session about cost-based optimizer. Again, picking up topics from the first session that we had a couple of weeks ago here at Redgate and allthingsoracle.com. Quick introduction about myself. I think I will not leave too many words about this. I'm an independent consultant and I'm available for the typical troubleshooting and design and application performance issues. So I provide in-house workshops and I can explain to you things like how the Oracle optimizer works and things and work through execution plans, and also give some ideas how you could do some performance by design, so not only about reactive troubleshooting but also proactive performance by design. And I think apart from that, James has already introduced myself. Just to pick those up that haven't watched the initial webinar about the optimizer. Here's again just the essence or the summary of what the cost-based optimizer is really about, or the question that you have to ask yourself and about your data that you are querying. There are basically three main questions that you need to address. The first thing is about the volume of data and how many rows you will get from your tables in your query. And the second important thing is where is the data, which means is the data scattered across the table that you're particularly looking for, or is it clustered together in a few blocks? So that is another very important question that needs to be addressed. And the third one is potentially if you have an idea about how well the data might be cached in the buffer cache which Oracle maintains. So these three questions are the crucial ones. And why are these questions so important? Because there are basically two main strategies that the optimizer can take. One is about trying to basically do everything in one big job. There you have, of course, the question, how big is this job, which is primarily driven by the question, how much data, how much volume. But you also have the second main strategy where you might run things in a iterative fashion using a small job approach, and there it becomes crucial. How many times do you have to run this small job? And the other question is how much effort do you have per iteration? So that is basically where the how many rows, how many times, and the clustering and caching issue comes into the picture. So you won't be surprised that the optimizer is basically trying to answer the same questions, but what I've tried to point out in the first seminar was that the optimizer is not addressing all questions to the same extent. It tries very hard to give good answers about the data volume and how many rows question, but it only addresses partially the question about how scattered or clustered your data is, and it doesn't incorporate caching at all in the current releases. So it only addresses this information partially that is crucial in order to arrive at an efficient execution plan. So this means that you might know your data actually better than the optimizer. You might have a better knowledge if you know your data and the application and the questions that you ask about the data. So that is basically the essence of it. And I've shown different use cases where I've demonstrated that the optimizer sometimes is rather clueless, and you really need to know more about your data and maybe sometimes need to help the optimizer, because even if all the information that it has is correct, it still might get it wrong, because some parts of these questions that I've mentioned are simply not covered or only partially covered. So that basically was the summary of the previous webinar, and if you're curious to learn more, then you can always watch the recording. Today I want to delve into some topics that I have only briefly mentioned or only haven't mentioned at all because there wasn't time. It's basically about things that the optimizer should know about. So I'm not talking about that part where the optimizer is clueless anyway, but I'm talking about these parts where the optimizer has some knowledge, and show you some examples why still the optimizer get it wrong. And we have one thing that I've already mentioned in the previous seminar briefly, that is the clustering factor that the optimizer might get wrong. Then we have a short section on general statistics and a longer section on histograms, why histograms might cause more trouble than you might expect. And finally, a short section on data type issues. So again, here are the same graphs that the same graphics that you've seen in the first webinar. This the upper area of this should represent an index range scan operation. So we basically go from the root to the branch to the leaf blocks, whatever height this index has. And once we have found the first leaf block that contains information that we are looking for, if we have to visit the table in addition to the index, then this might look like this. We do the index range scan operation, but we have to visit different table blocks. And this is basically what this scattering clustering, this clustering factor that Oracle knows about is about. It tells you whether you have a scenario like this, so you basically jump randomly from one table block to the other block while you scan the index. So the index scan operation here is usually a rather efficient operation, but you might have to jump to many table blocks, which means you basically end up with a lot of collateral data if you're only looking for a single row in a table block that may have hundreds of rows. So in worst case, for instance, you're looking for 1,000 rows, but you might have to visit 1,000 different table blocks in order to pick up this 1,000 rows. So this is basically a worst case scenario. And if you think about that, these table blocks are not in the buffer cache, but have to be read from disk, then you end up with something like, for instance, 5 seconds response time for a simple operation like that, because you have to wait for the disks to deliver each block. In contrast to that, we might end up with the same operation, but now we basically stay within the blocks and just jump from one block to the other block occasionally. So we can basically reference the same block over and over again, which also means that very likely this block will stay in the cache during the operation, so that we actually end up with a tremendous difference in the efficiency of this operation. So this is where the index and the table have very well clustered together, so that the table basically follows the index order. But this is of course only applicable to this single index. You might have another index with another order where the clustering factor or the clustering between index and table is very bad. So now we know that we have this clustering factor which is supposed to represent this information to the optimizer, so that the optimizer and Oracle knows is the index and the table roughly in the same order, or is it randomly ordered, so that any table visit that has to be done in addition to an index visit can be costed accordingly. Now the problem with this clustering factor is that there are various scenarios where this clustering factor might be wrong or might not be representative for the work that actually has to be done to pick up these table blocks via the index. And one very common issue is, because it is also recommended by Oracle, if you use automatic segment space management, this AESSM feature, which is default for a long time now, that is also recommended to use by Oracle. If you use that, then you might actually end up with a clustering factor that is not representative for the work. And another scenario might be that you use partitioning, or you actually use multiple free list groups with the legacy manual segment space management. And what is happening, basically, what it is all about, is that we end up with the same thing that we have seen now already, but we basically jump back and forth between the same blocks. So although it is correct that we change the blocks from row to row, or from most of the rows, we actually always visit the same range of blocks. And this is where the determination of the clustering factor might get it quite wrong, and it's a common issue, and therefore I'm picking it up again here. It's basically about visiting these same blocks, and as I outlined in the invitation for the webinar, I'm going to run through some demos now, and this one is trying to give you an idea about this clustering factor issue. So what I'm basically doing is I'm simulating a concurrent insert scenario. This ASSM clustering factor issue is basically only applicable if you really have concurrent inserts. And what I'm doing is I'm simply starting, in this case, 4 concurrent clients that are now going to populate a table concurrently, and I have a column that is populated via an sequence, and therefore this column is supposed to basically follow an monotonically increasing so I have run now this demo. It just took a couple of seconds because I've just inserted I think 40,000 rows or something like that. So I have 4 sessions, each inserting 10,000 rows concurrently. And I have created 2 indexes on the resulting table, one on this value that is populated via the sequence, and I have a random value that is populated via a random generator. So we can see that if we gather now statistics on this, that for the index that is based on the sequence-based column, we have very good clustering factor, which is rather close to the number of blocks that are covered by the index. And we can see that we have the random generated value, and we have a very bad clustering factor that is close to the number of rows, which basically tells the optimizer that visiting the table for an index range scan is going to be a rather costly operation. And I can even validate this. I can run here just a small script that shows us these 2 different scenarios very clearly. The first thing that I've done is I've simply extracted the blocks of the rows that correspond to the rows in the table and the index. So we can see that if I walk the tables simply via this index on this sequence-based value, that the values and the blocks point that if I follow the values, that I always almost land in the same block. So this is really showing us a very well clustered table if I look at this index and this table. So that looks really good. We see here these 4 concurrent processes. This also, so the run ID basically allows to differentiate between the different processes that have inserted the data, and we can see that although we have multiple processes, the data almost always is inserted into the same blocks. Of course, this is a problem if you have a high concurrency, because now you will end up with problems that multiple processes try to write into the same block. So therefore, if you have a highly concurrent system, you actually want to avoid this scenario. So there are things that you can do about it. You can start with these free list and free list groups things if you use MSSM, and ASSM is supposed to address this problem automatically, as we will see soon. And then I will do the following here. I just query 10% of this table via the index, and we can see that we actually have, when we use this index with the good clustering factor, that we really just read 10%, approximately 10% out of these 1,900 blocks. So it is, in fact, a very good clustered operation, a very efficient operation if we access the table via this index. Whereas if I repeat the same with the other index that has bad clustering factor, we can see that in fact just for reading 10% of the table we already had to read every single block of the table, because the table had approximately 1,700, 1,800 blocks. So this is a very inefficient operation, because we had to read that many blocks from the disk in this case, because I've flushed the cache before. So that shows us that the clustering factor that we see here that Oracle has determined is true. It seems to be representative of the actual work that has to be done at runtime. Now I'm going to repeat the same exercise using an ASSM table space, and we will see what is going to happen then. That was the wrong one, sorry. So the same again. And now if you look closely to these numbers, then you will realize that this supposedly well-clustered index now has a very bad clustering factor, and it will vary with each run. So it could have happened that I ended up with a quite good clustering factor. I could have even ended up with a worse clustering factor close to the 40,000. All right, so is this true? Is it really true that simply by switching to ASSM I now have such a bad clustering factor? So let's run this check script again and have a look at the results. So if you now look at the results here, you will notice that still the different processes write to the same blocks. So that hasn't changed really. But what has changed is that different processes start now writing to different blocks. And you can see now clearly this pattern that I have described in this, or tried to show you in this graphics, that we basically jump back and forth between the same blocks. I actually would have expected to see here 4, 1, 2, 3. So here we jump back and forth between 3 at least. It should have been 4. Not sure why this is now looking like that, but I think it becomes obvious. So we still have the same processes writing to the same blocks, but different processes have picked up different blocks. So that is why this is a deliberate design decision in ASSM, because it tries to avoid this concurrency that different processes try to write to the same blocks. But on the other hand, if I now derive the clustering factor simply by looking at these blocks from one row to the next row, well, I have almost in every row a different block. So the clustering factor algorithm that tries to determine the clustering factor basically says, oh, look, I have a different block. Next row I have a different block. So this is really a bad clustering. But if I now do an actual read operation on the data, then I see a different pattern. I can see that although I have accessed a lot of buffers, I still have read only 10% of the data from disk. So while it is true that the logical I/O part has increased significantly, the physical I/O part is almost the same as in the other scenarios. So this is basically where the clustering factor is probably not representative for the actual work, because most of these work, or most of the efficiency of the operation is driven by the number of physical reads that you have to perform. Logical I/O is pretty fast up to a certain level of concurrency, but the physical I/O is really a problem. So in this case, this clustering factor might not really be representative for the efficiency of the operation. And for many indexes that follow this pattern, that the data is inserted concurrently into an ASSM table space, you might end up with clustering factors that are way too high, and therefore the optimizer might actually reject to use the index and rather prefers a full table scan. So this is one of the issues why you might have this classic question, why is the optimizer not using my index? It might be just like this because it is a very common scenario. Whereas if we will look at the truly scattered data, we see the same pattern here. We have a lot of physical reads, so that follows the same as with the MSSM example. It's a truly badly scattered index table relation. But here we can see this problem, so that you might have the problem that the index is actually, the table access via this index is much more efficient than the clustering factor suggests. So basically that was this simple demo that I wanted to show you in that regard. You can find more about that. I think I have already mentioned that in the previous webinar. Here I have a blog post about this what if analysis for the clustering factor, where I provide some scripts that you can use to check whether your clustering factor actually corresponds to the actual work that will be done if you use this index table combination. So, right, I think I have even prepared something with partitioning, so I could run the same again and basically show you that if I use the MSSM variation but use, for instance, a table hash partitioning, then I might come into the same trouble. So repeating this thing. Yeah, so we basically see now that although I haven't used MSSM, sorry, I haven't used ASSM, but using MSSM, I'm getting now a bad clustering factor because now the table blocks again are spread across different partitions. So this is another point that you need to think about. How do you actually store your data, know your data, thinking about how is the data actually stored in the different blocks. Okay, enough about that. Short introduction to statistics. This is supposed to be a selection of things that I come across repeatedly. So what I'm still seeing is that people use analyze, compute, estimate statistics. This has been deprecated or basically de-supported a very long time ago. So if you have legacy code and that works, then of course don't touch it because it works. But if you see it in code that you have to touch or that you're currently working on, do not use analyze, compute, or estimate statistics anymore. Use them as stats. Then statistics. If you gather statistics or Oracle gathers statistics automatically, then you get basic statistics, which are table statistics, logs, rows, average, row, and there's not much to say or configure about these table statistics. These are always generated. But for the column statistics, you already have to differentiate. You have the basic column statistics that are the low and high value, the number of distinct values, and the number of nulls for each column. And you control this via this method opt parameter of the gather table stats call. And again, here's one thing that I see quite frequently. If you see a DBMS stats call where you have for all indexed columns, and maybe even for all indexed columns size 254, I assume that this is either a legacy thing, or maybe some internet pages still recommend to use that, because I see it that frequently. You should really question it, because you have to really understand what it means. It might be appropriate, but I think in most cases where it's come across, it is not reasonable, because if you do this, it basically means that you only get column statistics for indexed columns. For all other columns that are not covered by any indexes, you won't get any statistics at all. If you don't have any column statistics, the optimizer basically resorts to hard-coded defaults. It's basically completely clueless. So if you see something like that, think about it. It probably doesn't make sense and might cause you a lot of trouble. The default in previous releases for this column statistics configuration was for all columns size 1, and this size thing basically says, do you want extended, do you want histograms on the columns, and we'll come to histograms in a second, or do you only want basic statistics? So size 1 basically says no histograms at all, basic column statistics. Since 10G this has changed. You have now the default for all columns size auto, which means basic column statistics for all columns, and Oracle determines whether it will generate a histogram for a column or not, and I will explain this in a second what this means. So the point is here that it's a very good idea to be on the safe side, that you have at least basic column statistics for all columns. If you are sure that your columns are all indexed and all columns that are used in predicates, in group by, in order by clauses, then you can go for the indexed columns thing. But it's a very good idea to stick to the default, at least for all columns, that you get basic column statistics. This is still a common issue that I see many times. The point with the histograms is that the basic column statistics, this low value, high value, number of distinct, number of nulls, all these column statistics can in principle be generated with a single pass along with the table statistics. So basically Oracle has to scan the data, the table data, just once. This is not entirely true, but in almost all cases. If you have a table with many columns, more than 200 something, then DBMS stats might run multiple passes, but that's not that important. But the point is, if you have a histogram, this additional information for a column, each histogram that you generate requires a separate pass on the data, and therefore if Oracle is allowed to do it, if you use this default auto sample size option, then histograms will be generated with a very aggressive sampling, which means that Oracle will only look at a very small number of rows to generate the histogram. This is probably simply in order to address that you don't have that, don't lose that much time gathering these histogram information. But on the other hand, it means that the quality and the significance of the resulting histograms is probably rather limited. So that is basically a trade-off thing, and Oracle by default is rather aggressive with this sampling. So I will come to that later, what that means with what the sampling actually will cause. And then you should know, for the histograms there is not only a histogram, but there is either a so-called frequency histogram if you have less than 255 distinct column values, or you have if you have more than 255, then Oracle creates something that Oracle calls height balanced histogram, and I hope to explain to you what this height balanced histogram actually is. The important point to understand at this point is that height balanced is always basically a sampling of data. Even if you read all data, if you compute your statistics and read all data and do not perform any sampling, a height balanced histogram is basically always something that is a sampled thing. So it misses potentially important information, and that is already a very important point. So yeah, let's stop with the slides, because I've said I won't use too many slides this time, and start with the frequency histogram. What basically, to explain to you what is a frequency histogram about actually. So I have to clean up a little bit in order to not run out of disk space here. So, and then I will run another script and basically show to you what this frequency histogram is about. So the scenario that I'm reproducing here is rather simple to understand. We have a table with 1 million rows, and we have a status column which basically could represent something like processed, unprocessed flag or something like that, because that is a common thing that I come across quite frequently. So the nature of the column is that, for example, if you think about process data, most of the data is in status process. So the column information is very skewed. So most of the data is processed. In this case, 0 means processed. And only a few, if at all, items are in unprocessed or failed or whatever. So that is basically what our data looks like. So this is the typical scenario where you would read in common literature about Oracle or in the documentation. This basically requires a histogram, because Oracle otherwise will try to treat this 0, 1, and 2 as uniformly distributed data. That is basically what you get as an assumption from this basic column statistics. If you don't have a histogram, then you only have a low value, a high value, and a number of distinct values. And Oracle assumes that these number of distinct values is uniformly distributed between the low and the high value. That is the basic assumption of basic column statistics, and might be okay for many cases that you that the optimizer come up with reasonable estimates using these uniform assumption. But in this case, very likely not. And I have a second column which is very simple. There are just 2 values, and it's uniformly distributed. Each has 500,000 rows. I don't care about nulls here, which would complicate things maybe even further. So all the rows have column values for these 2 columns. Now, the first thing that you need to understand if you think about these histograms is that from version 10.204 and version 11G on, Oracle has changed the behavior of how histograms worked. And this new major change in behavior might cause you some trouble. Of course, there is a reason why this change was introduced, but there's always 2 sides, so it might be good, but it might be bad, and I will show you some of the bad examples. The first thing that you need to understand here is that this column here basically shows some inconsistency in the statistics that have been gathered. The point is that from 11G on, you have this new auto sample size, which allows to generate very precise basic column statistics very quickly, because it doesn't have to run group by operation, aggregation operation, which was necessary in the previous versions. So that is a very, very cool feature. And we can see that basically the sample size that is shown here is 1 million. So basically Oracle, for the basic column statistics, looks at all rows. We can also see that for our status column, which has these 3 distinct values, the basic column statistics tells us that we have 3 distinct values. So this is again spot on. But here is a problem. The histogram has been generated with a very aggressive sampling, just 5,000 rows out of 1 million. And even if you have, I think, 10 billion rows, it will still just look at 5,000 rows, which is just really a very tiny fraction of the data. And we only have found 1 value in this histogram, of course, because we have only looked at so few rows. So there is a problem. We have 3 distinct values according to the basic statistics, but we have only a single value in the histogram, which we can also confirm by looking at the histogram. So for the uniformly distributed column, you end up with a frequency histogram that is in the right ballpark. But for the status column, we basically miss our unpopular values. We only see the popular value. Now, here is the point. If you have such a pattern where you have just this single, very, very popular value, then this will cause you trouble with this new approach. Let's have a look at some of the estimates that the optimizer does. And there will be some surprising results. There's another point that I haven't mentioned yet. You might wonder why I have generated a frequency histogram on this column here, because it is clearly uniformly distributed, right? You have 500,000 rows each. What's the point in generating a histogram on this column? What you have to know is that if you use the default, this size auto thing, then Oracle will actually generate frequency histograms on all columns that get used as predicates, and they have less than 255 distinct values. So in fact, if you stick to the defaults, this uniformly distributed column will end up with a frequency histogram by default. So that is another important point, that the size auto default option might generate histograms where you do not expect a histogram to be generated. And if you see now what I have if you look now at the results, then you might see that this can cause a lot of trouble. The first thing is we look at the popular value of this uniformly distributed column. So 100 and 200 are the only existing values for this t-other call, right? So I look for 100 and the optimizer tells me 500,000 rows. This is almost spot on, 501,000. Now I look for a non-existing value, 150. There is no 150 in this table. You just have 100 and 200, 500,000 times. Yet the optimizer with a histogram tells us 250,000. This is way off. And two non-existing values, you end up with 500,000 instead of 0. So this is way off. So the problem is that since Oracle does this aggressive sampling by default, it doesn't trust its own information. The significance of the histogram has been lowered. It basically says, well, if the value is within the range of known values, I will basically use the least popular value of the histogram. In our case, the least popular value is still 500,000 times there. And I will simply use that as an point that I will use for the calculation. So if it's within the range of known values, then I will basically say, well, 250,000 might be a good idea, but it isn't a good idea. In the past, the old behavior of frequency histograms was very, very simple. You had just the values in the frequency histogram. If you were querying for values that were not existent in the frequency histogram, then you ended up with an estimate of 0, or basically 1 row. It was a very simple approach. What was there in the histogram, as you have a very clear picture about the data that is in the histogram, but you won't get any rows estimated for any values that are not represented in the histogram. Of course, due to the aggressive sampling that Oracle might perform, you might miss some important values, and therefore Oracle has changed this behavior in the latest releases, and now you have this problem here. So you have to think about really whether histogram can be helpful for such cases or not. So you have to be very careful. On the other hand, if you have non-existing values out of the range, then you are fine. The estimate is correct. Now let's have a look at our very, very skewed column. And this is this special case of this single very popular value. So for the single popular value, you get the correct estimate. Almost all data of the table has this very popular value. But we are now in the same trouble again here. If I ask for a non-existing value, it doesn't matter the range, because there is no range for a single bucket in a histogram. We only see this value 0 as very popular. Then you end up with, for this non-existing value, which should not be there at all and is not there at all in the table, again you get this estimate, and you get even a worse estimate if you look for 2 non-existing values. So that is really, really a problem, and you really need to know your data and understand what you're looking for, and check if you run into such trouble with the frequency histogram. So there are basically 2 important points to consider with a frequency histogram. If you have a frequency histogram that consists only of very popular values, then you have to be very careful with values that are in the valid range. You might get very bad cardinality estimates, estimates, and the same applies to this special pattern of having one very, very popular value and some very unpopular values. If you now look for this 10 and 20, you will get the same incorrect estimate. So that is also a problem that you need to be aware of. There are patterns that do not work very well with histograms, even for the frequency histogram that is supposed to provide you a very detailed breakdown of the column value distribution. Just to give you an idea how you could address such issues, if you have the option of using dynamic sampling, if the overhead is not too big, and if you can change the code maybe, or you can change the query, then you might be able to take advantage of dynamic sampling. So that is basically just an example here, that although the histogram provides this incorrect data, I can get a much better estimate here by using dynamic sampling. Unfortunately, as usual, there might be some problems. Again, here is just an example where dynamic sampling is not working very well, because although the estimate is not bad, it's not using the index. So again, you need to check your individual situation whether dynamic sampling can be helpful or not. I have written here on allthingsoracle.com an series on dynamic sampling, and it's also mentioned here what you have to do in order to cover such situations using dynamic sampling. So if you're interested, you might give it a read here on allthingsoracle.com, this dynamic sampling series. Okay, and well, we could repeat the same exercise. This time I go back to the previous behavior. There is a so-called fixed control that you could use to switch off this new frequency histogram thing. And if you now run the same queries again with this feature, then you will see that the estimates in this case are actually much better. So you can see we can still get for these existing popular value in these uniformly distributed, we get a correct estimate. For a non-existing, we get a much better estimate because it's non-existing, and it is simply non-existing in the histogram, and we are fine. And even for this pattern of very popular and unpopular values, you get much better estimates. Here you get this 1 million estimate, and here for the non-existing values you get a very good spot-on estimate. So you might actually, depending on the data patterns that you try to cover, you might even think about reverting to the old behavior, which you can do via this fixed control. And this is also explained in a blog post. There's another thing that you should know about histograms, that histograms are basically also limited not only in the number of values that they can cover, but also in the range of values that they can cover. So you might end up with very long strings or very large numbers, and if you have such extraordinary data, then histograms can cause a lot of problems, because the histograms won't be able to cover this very large column values. This applies to both strings and numbers, and you can read it here on my blog if you're interested, if you have such a situation. Okay, so what else do I want to tell about the frequency histogram? Yeah, there's a very important point that I haven't mentioned yet. We can see that we have in our histogram, we have this only this single value covered for this for this very popular value, and the other values, this 1 and 0, are not in the histogram at all for this status column. Now, if I run the statistics calculation a couple of times, and I have to do it maybe several times, then we will end up eventually with something like this. Now you have the coincidence that although we have aggressively sampled the data, we end up with data that is now covering also a very unpopular value. Now if I run the same statements again on this status column, I now have the issue that I basically get the correct estimate, which is not a bad thing, which is a very good thing. But the problem is, what I wanted to show here is that with this scenario and this sampling performed, you can end up with a very non-deterministic behavior. Maybe once you get the luck, you are lucky and you get these unpopular values. Maybe the next time you gather statistics, you don't get this unpopular value into the histogram, and the results will be completely different regarding the estimates. If you remember, this estimate here was 250,000 and this estimate here was 500,000 rows. Maybe the other day where you again gather statistics, you get now an estimate of 1. So this is a problem because it can cause you a lot of instability in your system. So that is also very important to consider with this sampling of the histograms, that you can have problems with the non-deterministic behavior of the results of the sampling. Okay, so what can you do about it? I've already said you might try dynamic sampling. just to have mentioned it. Another idea for this thing with this very, very popular and unpopular thing is that you could do something like this. You could add a function-based index or a virtual column that basically covers only the unpopular values. If you're interested in only the unpopular values, which is, for instance, very likely for this processed thing because you're looking for unprocessed data that you want to pick up, then you have a problem with these estimates of this histogram, because this histogram will cause that the unpopular values will be treated as very popular to this issue that I've outlined. You could, for instance, follow this approach here and generate a virtual column that only picks up the unpopular values, and then you will get very good estimates simply because you're only interested in the unpopular values. So this is again this mantra that if you know your data, then you may be able to help yourself very efficiently using dynamic sampling, using virtual columns, whatever. Just to give you an idea what you can do about it. You can download the scripts afterwards, what we will post, and you can try it then yourself to see the results. Then let's have a look at height-balanced histograms to give you an idea what the problem with height-balanced histograms can be. In this case, I will create a different data set, basically just a very skewed data set again. This time we have 10 million rows, therefore it will take a tad longer to generate the data, and it basically looks like this. So we have 100 very popular values, each with 70,000 occurrences, starting from 1,000 to 100,000. So 100 very popular values with 70,000 occurrences each. But then we have a large gap in the data, the column value, and starting with 7 million, we actually have, I don't show you these, then 3 million distinct values. So again, clearly something that you probably want to tell the optimizer about. Of course, if I now ask the optimizer for particular values with this uniform assumption of the optimizer, we basically end up with something like this. So the first thing that doesn't have a comment here is the estimate for a range. So I'm looking for a range that actually does not have any data at all. Between 6 million and 6,100,000 there is no data at all, but you get an estimate of 100,000, which is of course way off. And you can see here all of our values are basically treated the same. This is the issue of having the assumption of uniformly distributed column data. So let's generate a histogram, and this time, since we have that many distinct values, we cannot generate a frequency histogram. It's simply not possible because we have a limitation of 255 or 254 values that can be covered by the histogram. So if I now generate a histogram, I end up with this so-called height-balanced histogram. And now let's have a look at our estimates again. In particular, if we look for these popular values, 10 of them, just 10 of them I have checked, and one unpopular value I have checked. So now consider what happens if you had the situation that 5,000 is the value that your application is mostly interested in. Now have a look at what happened with the height balance histogram. The cardinality estimate for the very popular value 5000 actually got worse, because in the previous screen we can see without a histogram we had a very bad estimate of 3, but with the histogram in place for this particular value I now have an estimate of 1, but for other values I have a quite reasonable estimate. So that's really bad. That's really bad luck, because height balance histograms cannot cover all values, so they might miss important values. And this is exactly what happens with this data distribution. Again, if you know your data and you know that you're interested in a particular value, then you need to ensure that the statistics really allow the optimizer to tell that it gets an estimate in the right ballpark. So what is even worse here is if I now repeat the statistics generation without actually changing my data, and I repeat looking for our popular values, then you might be surprised that you again get a completely different picture of data. So now I have other values that have been missed, and if I do it again probably a couple of times, then I might even end up with our value that we're interested in, this 5000. This time I have 5000 with a very good estimate, but again the problem is instability. One day you have this value, and the other day you have this estimate for the same value. It's basically flip-flops between 1 and 80,000. That is really a bad thing, because again you will have troubleshooting why did I have this kind of execution plan on that day, and why did I have a different execution plan on the other day? It might simply have been that you have been lucky one day and unlucky the other day. So height balanced histograms have this problem. Even if I gather the statistics within compute operation, and I need to use a little bit more horsepower for gathering statistics on that big data set. Therefore I use parallelism here. Hopefully that it is using memory and doesn't take too long to get the statistics gathered. So I have now computed the statistics. You can see here that I use this estimate percent null option, so which means do not sample, read all data. Even if I compute the statistics and I repeat the exercise, you will see that our important value 5000 is still missed. So height balanced histograms, you need to question whether they really help you in the way that you expect histograms to help. That is basically what I wanted to show you here with the height balance histograms. And I've prepared a graphic, a picture that hopefully allows you to understand why this happens and what the problem with the height balanced histogram is. Height balanced histograms in Oracle is an interesting name, but it is rather simple how it works. You get basically the data ordered by the column value. You can see this here. We start with column value 1000, then you have 7000 repetitions of this value, then up to 140,000 you have 2000, 3000, and so on and so on. And what the height balance histogram basically does, it uses the number of buckets that you have provided. I've used for simplicity in this case 250. The maximum value would be 254. So it doesn't really change the outcome. But it basically creates the number of buckets, 250 buckets in this case, that cover the same number of rows. And the only information that the height balanced histogram basically consists of is the information about the endpoint value when the bucket ends. So every 40,000 rows, Oracle basically records the value that it sees. So at row 40,000 it sees 1,000. At row 80,000 it sees 2,000. At row 120,000 it still sees 2,000, and so on and so on. So the only thing that Oracle can tell from a height balanced histogram is that a value might be popular, and the value is only then popular if it shows up for more than one consecutive bucket. So 2,000, for example, in this case, is you can tell something about the value 2,000 from this height balance histogram because it shows up in more than one bucket. We can see the same about 3,000, we can see the same about 4,000, but 4,000 is already a very dangerous value, because if you can see at 280,000 rows we have the switch from 4,000 to 5,000, and it's exactly on this 280,000 also the bucket changes from one to the other. So assume that your data distribution changes slightly. Now you have maybe 71,000 values of one the other day. Then 4,000 might be popular, or it might not be popular anymore if you have only 69,000 values or something like that changed in the value distribution. So this is the problem with the height balance histogram. Depending on your data distribution, you might have these flip-flops, and this is where your height balance histograms might not be that useful as you would expect. So you cannot simply assume that Oracle generates useful histograms because it doesn't know the data the way you know it. It simply assumes with the size auto function, for example, that if it gets used in a predicate and you have a non-uniformly distributed data distribution in the column, or you have less than 255 distinct values, then it will generate a histogram, but it won't check if the questions that you ask about your data are actually answered correctly by these histograms. And this is where you have to be very, very careful with histograms. This is, for example, a data pattern that simply won't work very well with height balanced histograms depending on the questions that you ask about the data. Notice that height balanced histograms, I forgot to mention here, you can see that this problem that is caused with this 5,000 value. 5,000 is unlucky because 5,000 will only be show up once for these buckets. So, well, 5,000 is not popular, and therefore it gets treated the same as any other unpopular value. And since we have 3 million unpopular values, in addition to these 100 popular values, this very popular value gets treated very unlucky because it basically gets the same estimate as these unpopular values. So, well, that can cause you a lot of headaches. One thing I wanted to mention about height balanced histograms is that they can still be very useful, even if they don't cover your data for the questions that I have asked here very well. They can cover your data very well for other questions like range questions. This is what the optimizer basically sees about the value distributions based on this height balanced histogram. So if you ask for data in certain ranges, then the height balanced histogram will be very useful. So it can tell, for example, that between 100,000 and 7 million there's almost no data, and between 7 million and 10 million we have uniformly distributed data, and we have this peak here, this spike in the lower range of values where we have these very popular values. So you can see this if I run a corresponding query where I ask for these ranges. Then I will get now very good answers, although I didn't get very well answers for my value 5,000. I get a very good answer for the non-existing values now. You might remember that we got 100,000 as estimate for these non-existing values without the height balance histogram, but I get a very good estimate now with the height balance histogram that there is almost no data in this range. And I also get a very good estimate if I run the same for these popular values for the range query. Then I get a very good estimate of 7 million rows because I have 100 values each covering 70,000 rows, which is 7 million, which is very, very good estimate. So height balance histograms can be useful, but height balance histograms can also be cause a lot of trouble. It again depends on what questions you ask about your data. And what could you do about if you have such a data pattern like the one I've shown now? Again, you could use things like dynamic sampling, or you could have to create a histogram manually that covers the important data that you are asking about. And I've again collected information about that. Jonathan Lewis has a very good a couple of very good blog posts about how you can generate histograms manually, how you can fake histograms in principle. So you can look up there how you can do this, and you might have these kind of data distributions in some cases where you actually need to generate a histogram manually, because otherwise, in my example here, the value 5,000 won't simply be covered very well by the statistics collection. So no matter how you do it, it will either flip-flop between good and bad, or if you use the compute option, it will not show up as popular at all, but at least consistently. But that probably doesn't help, because you want to see it as popular, or at least the optimizer should see it as popular. So that is basically what you have to think about with height-balanced histograms. You are running the danger of missing important information. And it doesn't matter how much effort you put into gathering them, the data patterns might simply be in such a way that height-balanced histograms do not cover them very well. All right, so that is basically what we've already seen in the beginning. This is what the data distribution looks to the optimizer if you do not have the height balance histogram. So for this kind of question with the range, it can be very helpful. Okay, so finally, just 2 quick demos, then I'm done, because it's also something that I come across very, very often. I don't know exactly why, but I get this question rather often. Consider, for example, that you have the question, how should I store the data in the database about the data type? And one thing one question that I get quite frequently is, couldn't we store a date in numbers? Because numbers, I don't know why. Maybe they save one byte per row or something like that. So I get this question. I'm quite surprised that I get it that often, but it's a question that is raised frequently. And in principle, it's very easy. Oracle doesn't have that many different data types, so, and I think you should simply make use of them very clearly, that you use the data type that is appropriate. And here is just an example, very simple and small, where I simply generate a single, uniformly, basically a single column with just holding dates for 5 years worth. So starting from 2000, then up to December 2005, I think. And I just generate this table, and then we will have a look at some estimates. Well, remember that the data is very straightforward. You have simply each row covers one day, and we have 1,800 rows. So I'm asking a simple question about that data. I just ask how many rows will I get for 7 days, so the 30th of December 2002 to the 5th of January 2003. If I ask this data, and I didn't generate any fancy statistics, just basic column statistics. If I ask this question using the date column, then I get a very good estimate, 8 instead of 7, so which is very, very close. If I ask the same question by storing the same information in the number column, I get a completely off estimate. So in this case, 400 instead of 8. So it is just like that. If you start abusing the data types, then you get all kinds of issues, but on top of that, you simply will get issues with the optimizer. I know that there are probably these database agnostic applications that simply store everything in a number or everything in a character field, but it's a very bad idea for several reasons. But from an optimizer perspective, it's also a very bad idea because it's basically asking for trouble. You will get bad estimates. That is as simple as that. And one final thing I will show you is that also I come across quite often, and this has also been covered to some extent by Tom Kite, are these implicit data type conversions that might happen. So let's create a very simple table, and I have uniformly distributed the data here, just 10 occurrences for every value for 100,000 rows, right? And if you have a mixture of, for instance, Unicode columns and non-Unicode columns, then you can end up with something like this here, where you basically get an estimate for this. And the problem here is that instead of the estimate of 10, which you would get, normally you get a completely way of estimate. And why is this the case? Because you have these implicit data type conversions, in this case between Unicode and non-Unicode data. So once again, be careful with the data types and be careful with this implicit data type conversions. They not only open up things like these evil things like SQL injection and other things that Tom Kite has talked about, but they will also confuse the optimizer potentially. So you have to be very, very careful with these data types and how you use them. Okay, so I think I'm almost done. Here is the summary of this today's session. Clustering factor I've shown to you. There are issues that Oracle might get the clustering factor wrong, and I've shown you ways how you could verify whether the clustering factor that the DBMS stats gathers is correct or not. Then in principle, in general, Oracle is not aware of the questions that you ask about the data, so it might start generating histograms, for instance, that are not appropriate for the data and the questions that you ask about the data. Therefore, one idea might be that you want to use for all column size 1 as a default. Do not generate histograms at all and only generate the histograms where you actually need them. But then you need to know your data again. You cannot rely on Oracle to generate the histograms for you. You may have to use the old behavior that I've outlined for these non-existing values where Oracle in the recent releases doesn't really trust the frequency histograms. You may get better results if you revert to the old behavior where Oracle trusts more the content of the frequency histogram. Then there are data patterns that I've shown to you that simply do not work very well depending on the questions that you ask about the data. Then you might have to actually generate histograms manually. And I've shown to you links that you can also download then together with the remaining webinar material where you can see how you can actually do this, manually generate histograms. And then do not forget about the other options that you have. You might get better results using dynamic sampling, using virtual columns, function-based indexes, extended statistics. These are basically all about the same technology. And you need to know your data and your questions that you ask about the data. That was also the mantra of the previous seminar. Okay, so before I forget it, we go back to the beginning of in this book here, this Expert Oracle Practices, Jonathan Lewis has written has contributed a very excellent chapter about statistics generation that also covers these things about histograms and that you might need to manually generate them. So I can only recommend this as a read. It's a very, very well written chapter about basically most of the things that I've covered in this webinar. And now we are, I think, with the question and answers. James, back to you.
Hi Randolph, thank you. I thought that was absolutely fantastic, and thank you for going into so much detail. And it's nice to see that most people have stayed on for the whole session. I understand a few people might have left because it was getting close to the hour. But thank you. Okay, so let's move on to the Q&A. There's a couple of questions, or one particular question that I just wanted to ask straight away. That's to do with the scripts that you're using. I know we published the scripts from the first webinar. Are you able to, or am I able to provide these scripts for the audience as well?
Yes, of course. All these scripts that I've used will be made available for download, so you can reproduce all these things that I've shown. This will all be available here.
Fantastic, thank you. Okay, so the first question we've got is from Jürgen Schauser. Thank you, Jürgen. He's asking, do we have to read the same block from the disk again when it is already read from disk, or does the index know that it is in the buffer cache already?
Well, it's not actually the index that knows anything about this, but yes, in principle, I have forced in my script that the data has to be read from disk again and again. If I had done it once and repeated the same experiment without flushing the cache, then the disk reads wouldn't have happened. So that is, of course, true, but it doesn't change what the experiment was supposed to tell, that if you have a sufficiently large table, you won't be able to keep all the data in your cache, and you will suffer from these physical disk reads.
Thank you, Randolph. There's also a couple of questions that are quite general about different types of histograms. Do you have some advice on where people could go to find this out? I think it's probably quite a large topic to cover in the Q&A.
About histograms, yeah, I think I have tried to cover that in the summary already. I think that you have to be aware of the most important point, I think, is what should be taken away from this seminar is that you cannot rely on Oracle that it automatically generates histograms that are always useful. You need to understand that there are various limitations in the way Oracle gathers, samples data, and the way the data is then represented in these histograms. and you need to check whether it really makes sense to have histograms on certain columns depending on the questions that are asked about the data. So you might come, depending on your application and the data you have, you might come to the conclusion that you better work without histograms for most of your data and only generate histograms for those columns where you have proven that they actually are helpful. So that might be one approach, and it's also outlined in this chapter that I have mentioned by Jonathan Lewis, different approaches how you can approach this thing about histograms. But the important takeaway is that even frequency histograms, which are supposed to provide a very precise and exact picture about the data, can cause trouble depending on the questions you ask and how Oracle has gathered the statistics. So this is just a word of caution. And this size auto thing, where Oracle automatically determines when to generate histograms, is not always giving you good usage of histograms.
Thank you, Randolph. So we've got a question here from Richard Kinreid. Thank you, Richard. And he's asking, are there restrictions for online reorg? For example, you might be able to see this actually in your own question panel, Randolph, DCIDX. Are there improvements in this area on 11G-R2 over 10G-R2?
Well, actually, it's not a topic that really fits into this optimizer thing. Actually, I think there are improvements, various improvements with each release regarding the online reorganization capabilities. Off the top of my head, I cannot answer this particular question whether descending indexes are now capable of being reorganized online. But it's not really related to what I've talked about.
Okay, thank you. Do you have any general advice about the optimizer, improvements to the optimizer from 10 to 11?
Well, I can. That is a very good question, and I haven't prepared that, but it's something that I could provide as some of the things that we could provide afterwards. There is a very good white paper by Oracle, by the optimizer group, what you have to take care of if you want to do an optimal migration to 11G, in particular with regards to the changes in the optimizer. And it is a quite large paper with a lot of details, but it gives you really the complete picture what you can do, which preparation steps, and what you should, which gotchas you have to watch out basically when you do this kind of upgrade. So I haven't prepared that, but it's a very good question, and there is lots of material available from Oracle.
Thank you, Randolph. Next question from Amir Hamid. Thank you, Amir. If using free lists and free list groups is bad for the clustering factor, then how should one configure these parameters in a rack environment without impacting the clustering factor?
Yeah, well, I think you have probably addressed this in the other way around. The point is that you probably will have a good reason that you use free list and free list groups in the rack environment, or basically you will end up with the same situation if you use ASSM instead. The point I try to make here is that you actually have to correct the clustering factor in such cases. So you probably have to use a particular setting for free list and free list groups, otherwise your concurrency in the rack environment will be impacted. So that is probably not an option to say I use a different setting just because the clustering factor is bad. You need the setting because you otherwise don't scale in the rack environment potentially. And if you need these settings, then you need to check whether the resulting clustering factor is incorrect, and the scripts and this blog post that I've pointed out allows you to check the clustering factor, and you might need to manually correct then the clustering factor so that the optimizer has a better idea of the actual work.
Thank you, Randolph. whilst we're on the topic of clustering factor, Sergi's added a comment here asking whether is the only way to reduce clustering factor to recreate the table.
Yes, that is a very good question, because quite often people are struggling to understand whether you get a different clustering factor by rebuilding the indexes, or what you can do about it. In fact, it's possible to arrive at a different clustering factor statistics by rebuilding the index, but this is merely a side effect of fresh statistics that have been generated. In principle, if you think about how the clustering factor is determined, as long as the table order doesn't change, the index order is fixed, because you define the index order by the index definition. So no matter how often you try to recreate the index, the relation between the index and the table will stay the same, unless you start reordering the actual table data. But this is something that you need to think about very carefully, because maybe you screw up the clustering factor of other important indexes. So I've tried to address this thing in the basics webinar, where I point out that you can influence the way the data is clustered and scattered by using the different storage options that Oracle provides, like clusters, index clusters, hash clusters, like index organized tables. If you think about you want to optimize your query load for a particular type of query and the questions that you ask about your data, then you should start thinking in the way maybe you should start thinking about using clusters or start using index organized tables. But this needs to be evaluated very carefully, because if you do not use it appropriately, then you might actually end up with worse performance than by sticking to the normal heap organized tables.
Okay. Thank you, Randolph. This is a question from Harverinda Dylan. I hope I pronounced that correctly. He's asking, if we're looking at the explain plan, can we determine what the problem is because of histograms?
Well, you can determine this by looking at the explain plan output if you have knowledge about your data. So if you know your data and the particular question that you ask about data, then you can have a look at the explain plan and can see whether the resulting cardinality estimate is in the right ballpark. That is the thing about the histogram. So if what I've showed in my demonstration, if I'm interested in this particular value 5,000, and I know that this value shows up 70,000 times in my data, and I see in the explain plan that I get an estimate of 1, then I can definitely tell something about this. Of course, if you do not know your data, then you can't really tell from the explain plan output if there is a problem or not.
Thank you, Randolph. The next question from Jean-Christophe Dolce. Thank you, Jean-Christophe. I think what Jean-Christophe is trying to ask, apologies, it's a little bit confusing for me here. It's asking about tackling data distribution. Can you tackle data distribution since a function-based column could not resolve all the cases? How would you tackle data distribution?
Yeah, I think it's more related to this this data distribution issue that I've outlined with the height balanced histogram, and that is maybe one of the cases where we have to revert then to different techniques. You might have to use a handmade, handcrafted histogram where you make sure that the values that you ask for are certainly represented well. You could use this dynamic sampling. Maybe depending on the particular situation, you can use this virtual column function-based index approach. So there are ways how these problems can be tackled. But of course, the first thing is that you need to be aware of that you have such a problem. And that was one of the purposes of this webinar.
Okay, thank you, Randolph. So the next question here we have from Cherklusku Hoira. I hope I've pronounced that correctly. is asking, in dbms_stats, if you set the parameter to null, does that mean that Oracle will determine the correct value?
Well, I think this probably relates to these sampling percentage that you can set, I believe. There are many parameters in DBMS stats, so many of them can be set to null and left as default. So, but I now pick up this point with the estimate percentage, and as I've shown with this height balanced histogram, even if I do not sample the data at all, but I really go through all the data, I compute the statistics, reading all data, I might end up with a data distribution that simply is not represented well with this height balanced histogram, simply because the height balanced histogram by definition has to miss values and might miss important values, and you might have such an unlucky situation where you gather, even without any sampling, gather all data, and you still end up with the wrong answer by the optimizer. So that's what I wanted to point out. Not in every case you solve the problem by gathering statistics on all data, and in most cases you don't have actually the resources and the time to wade through billions of rows and then to end up with a correct result. So we probably don't have the time and the resources to do that.
Thank you, Randolph. There are a few questions here about the webinar recording and the resources that Randolph's highlighted. So all of this will be available on the Redgate website at redgate.com/oracle-webinars. I'm hoping I can get the video recording up tomorrow. It is being recorded at the moment. As you've registered for this session, I will be sending you an email as soon as the video is ready, but please feel free to check out redgate.com/oracle-webinars in advance to see if I've put it up. Okay, so a few more questions to get through today. Next question from Timmy Leung. Thank you, Timmy. He's asking, could you illustrate the number column with timestamp data type?
Well, yeah, in principle, this you use, if you think about storing a timestamp in a number column, then I'm pretty sure you will end up with the same issue. Yeah, so the problem is simply that these gaps that are in the data, in the number data that represent a date or a date time or a timestamp, these gaps are simply not obvious to the optimizer, and therefore the estimates based on this number representation very likely will be wrong. Now, gaps are, even if you have unique values, gaps are one of these not very well known cases where histograms can also help. So it's not only this very skewed data pattern, also this gap pattern. If you do range queries, typically you use dates with ranges. For these range based queries, histograms can even be very helpful to the optimizer if you have a unique data, because unique doesn't prevent you from having gaps in the data. And it's exactly these gaps in the number data that prevent the optimizer from getting the estimate using the incorrect data type right. Now you could argue why not generate a histogram on the data, because the histogram will show the gaps in the data. That's true, and the thing that I've demonstrated, if you generate a histogram on this number column, then the estimates will be much better, but then you are back to square one, because you might have a data pattern that is not represented very well using a histogram. So I don't see a point in using the incorrect data type. You better use the correct data type, then you don't have a need for a histogram.
Thank you, Randolph. I wonder whether you could have a quick look at the question panel. There's a few more questions on statistics, but I feel that we've covered quite a lot of that, and I don't know whether there's any final remarks you'd like to make based on the questions around statistics, or again, any resources that you could point the audience to find out a little bit more information.
Yeah, I see here one question. Is it enough just to collect statistics with DBMM stats every week, for example, to reach the best explain plan for queries? I think this is an important point, because that's also something that I've tried to explain in the basics webinar. It doesn't matter how fresh your statistics are if they do not allow the optimizer to answer the questions that you ask about your data correctly, then it doesn't matter how often and how much resources you throw at gathering statistics. So no, it probably is not something that you can rely on. Even if you gather statistics rather often, you still might end up with situations where the optimizer gets it wrong because the estimates are incorrect, because the statistics do not represent the data in the way you ask questions about it. So that is simply the point, that if you really want to get it right, you need to know your data. And this is also the reason why think that it is an application developer's task to get the application performing, because the application developer is supposed to know about the application and the data. It's not a DBA task, but that's a topic for another day.
Thank you, Randolph. And on that point, Elamaran El Lango, I hope I pronounced that okay, has asked that how often do we need to gather stats on a huge database, say over a terabyte? I mean, does the size of the database actually matter?
Yeah. I don't see the question. Can you just repeat?
So it's the last question. How often do we need to gather stats on a huge database, say over a terabyte in size? And I actually just wondered whether the size of, how much impact does the size of the database have?
Yeah. Yeah, well, of course, that's the point, that many databases are huge, and you don't have the resources to gather statistics in a way that would allow to get very precise answers, and then even more, you have the need to understand what questions you ask about the data, so that you can ensure that even with the sampling that you might need to perform, that you get the right answers. For very large databases, you also come into the question about partitioning, and that's also something that I could provide as an afterthought for this webinar. There's a link there's this collection of information about how to gather statistics for very large tables having partitions. And this is by Doug Burns. And Doug Burns has done a very good collection of information how to gather statistics on partition tables, because that's a very complicated and confusing topic. So that might be something, a link that is worth to provide regarding that question.
Absolutely. And what I'll do, I'll put that on All Things Oracle today. So I'll find this post by Doug Burns and link to it from All Things Oracle. Similarly, the recording of this webinar will sit on the Redgate website, but it'll also sit on allthingsoracle.com as well. And the great thing about putting it on All Things Oracle is you'll have the ability to ask some questions there, which, again, I think Randolph will be able to provide a little bit more information and point you in the direction of some more detailed resources. Okay, so I'd just like to thank everybody for the questions. I think it's always a really great part of the webinar. I'm sorry if we've missed a couple of them, but again, hopefully we can answer these on All Things Oracle. The slide we've got up on the... Sorry, I've just realised that we're actually still on Randolph's screen, so if you just bear with me. Okay, so the slide we have up on the screen now, you should be able to see our contact details. So you can contact Randolph via sequeltools-++.org. Please check out the content that's available on Randolph's blog at oracle-randolph.blogspot.co.uk. If you are a regular visitor to allthingsoracle.com, you'll probably notice that I do link off to resources on Randolph and some of the other experts' blogs. Please, of course, visit allthingsoracle.com. You can follow me on Twitter, where you'll hear about upcoming webinars, as well as webinar recording and other things that I find interesting, at All Things Oracle, and my direct email is at james.mercer@red-gate.com. I'd be really glad to receive any feedback on the webinars and the other educational resources that I'm providing for the community. I'd be particularly interested to hear of ideas for topics that you'd be interested in. So please email any feedback and any ideas to my email address that you see on the screen there. Okay, so I'd just like to say a big thank you to Randolph once again for taking a session on the cost-based optimizer. I hope you've all enjoyed it. Thank you, Randolph.
Thank you, James.
Thank you, and have a nice day.